On the morning of August 17th, 1943, a Focke-Wulf 190 fighter roared across the skies above Tarnewitz on Germany's Baltic coast. The pilot lined up his sights on a steel target plate positioned over the water, pressed the trigger, and watched his 20mm MG151 cannon shells arc toward the target. The armor-piercing rounds struck the 20mm thick steel plate at 300 meters. Most of them bounced off. Some penetrated, but barely. The test engineers recorded the results with careful precision. 20mm armor plate, 300 meters, 60-degree angle, penetration, 10 to 12 millimeters. The results were expected. The MG151 had been in service since 1941. German engineers knew its capabilities. They knew its limitations. But what happened 3 hours later would challenge everything they thought they understood about aircraft armament. An American P-47 Thunderbolt had crash-landed near Hamburg 2 days earlier. The pilot had bailed out. The aircraft was mostly intact. Luftwaffe salvage crews had transported it to Tarnewitz for weapons testing. The Thunderbolt carried 8 Browning M2 machine guns, each loaded with a mix of ammunition types. Among them were rounds with silver-tipped bullets, armor-piercing incendiary ammunition, .50 caliber API rounds. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you're watching from today. The test engineers at Tarnewitz were ballistic specialists. They had evaluated every major aircraft weapon Germany possessed and many captured Allied weapons. They understood the physics of armor penetration. They knew that larger caliber weapons with heavier projectiles generally penetrated more armor than smaller caliber weapons. That was basic physics. The question was whether American 50 caliber ammunition followed that same rule. They mounted the captured Browning guns on test fixtures. They positioned the same 20mm steel plates used in earlier tests. Same angle, same distance. They loaded belts of captured American 50 caliber API ammunition and prepared to fire. When the first burst tore through the 20mm plate like it was sheet metal, the engineers stopped the test. They examined the plate. Clean holes. The API rounds had penetrated completely. At 300 meters, at 60 degrees, the same armor that had stopped their own 20mm cannon fire. They ran the test again with fresh plates. Same result. The American 50 caliber armor-piercing incendiary ammunition was penetrating 20mm armor that German 20mm MG151 cannon shells could not reliably defeat. That should not have been possible. But the evidence was lying on the test range in front of them, punctured steel plates that told a story German command would not want to hear. The Tarnewitz test facility had been built in September 1935 as part of the Luftwaffe's network of specialized weapons testing stations. It was one of 4 Erprobungsstellen, or test establishments, headquartered at Rechlin, the Luftwaffe's primary aircraft evaluation center, located 100 kilometers northwest of Berlin. Tarnewitz itself was constructed on an artificial peninsula at Boltenhagen, on the Baltic Sea coast. The entire peninsula, approximately 1 kilometer across, had been surfaced with asphalt. Firing tests were conducted over the water between the test site and Pole Island. This allowed weapons engineers to test aircraft guns, autocannon, rockets, and experimental armaments without worrying about where the bullets landed. By 1943, Tarnewitz had become the Luftwaffe's primary facility for testing aircraft weapons. Every new gun design went through Tarnewitz. Every modification to existing weapons was evaluated there. The engineers who worked at the facility were among the best ballistic specialists in Germany. They had tested the MG-17, the MG151 in both 15 and 20mm versions, the MG131, and various Bordkanone heavy cannon designs ranging from 37mm up to 75mm. They also tested captured Allied weapons, British Hispano 20mm cannons, Soviet Schwack weapons, American 50 caliber Browning machine guns. The engineers approached these tests with professional curiosity rather than nationalist pride. Their job was to determine performance characteristics, identify strengths and weaknesses, and provide data that German designers could use. The American 50 caliber Browning had been encountered before. German forces had captured numerous Allied aircraft throughout the war. P-38s with 450 caliber guns, P-40 Warhawks with 6, Spitfires that the British had equipped with Browning machine guns under license. The weapons themselves were well understood. What had not been fully appreciated was the ammunition. American forces used several types of 50 caliber ammunition: ball ammunition for general purposes, armor-piercing ammunition with hardened steel cores, tracer ammunition for observing fire, incendiary ammunition for setting fuel tanks ablaze, and armor-piercing incendiary ammunition that combined both capabilities. The API round was designated M8. It consisted of a steel case, a primer, propellant, and a projectile weighing 647 grains. The projectile had a hardened steel core designed to penetrate armor, surrounded by incendiary material that ignited on impact. The bullet left the barrel at 2,930 feet per second, carrying over 13,000 foot-pounds of energy. German engineers knew these specifications from intelligence reports. What they had not fully tested was how that energy translated into armor penetration when fired at combat ranges against typical aircraft armor thicknesses. The Tarnewitz test in August 1943 was designed to answer that question. The test protocol was standard. Engineers set up steel armor plates at measured distances. The plates came in various thicknesses: 8 millimeters, 12 millimeters, 15 millimeters, 20 millimeters. These thicknesses represented typical armor protection on German and Allied aircraft: cockpit armor, engine cowlings, self-sealing fuel tanks with armor backing. The plates were positioned at 60-degree angles to simulate oblique hits, which were more common in combat than perpendicular impacts. This was important because armor performs better against angled shots. A bullet striking at 60 degrees must penetrate more material than one striking at 90 degrees perpendicular to the surface. The captured Browning M2 was mounted on a rigid test stand. Belts of captured American 50 caliber API ammunition were loaded. The engineers verified the ammunition was genuine American production, not German copies or experiments. They wanted to know what German pilots were actually facing in combat. The first test series used 8mm plates at 500 meters. The API rounds punched through easily. No surprise there. 8mm was relatively thin armor. The test continued with 12mm plates. Still penetration at 500 meters. Still expected. 15mm at 300 meters. Penetration beginning to be impressive. Then came the 20mm test. This thickness represented serious armor protection. German fighters used 20mm armor to protect pilots. Engine cowlings on bombers often used 20mm steel. Self-sealing fuel tanks frequently had 20mm armor backing. This was armor designed to stop machine gun fire and resist light cannon shells. The American 50 caliber API rounds went through it cleanly at 300 meters, at 60 degrees, multiple hits, consistent penetration. The engineers checked their equipment. They verified the angle measurements. They examined the plates for defects. Everything was correct. The American ammunition was simply performing better than expected. They compared these results to data from MG151 20mm cannon tests conducted earlier that same week. The German 20mm AP projectile could penetrate only 10 to 12 millimeters of armor at 300 meters at 60 degrees. The American 50 caliber was penetrating 20 millimeters under the same conditions, nearly double the penetration from a smaller caliber weapon. The physics should not have allowed this. Armor penetration depends on several factors: projectile energy, projectile cross-sectional area, projectile hardness, and striking velocity. A larger projectile with more mass should penetrate more armor, assuming similar construction and velocity. But the American 50 caliber API round was outperforming German 20mm AP ammunition, despite being smaller. The answer lay in the design philosophy. German engineers had optimized the MG151 for explosive effect rather than armor penetration. The 20mm cartridge was created by expanding the neck of the 15mm MG151 cartridge to hold a larger explosive shell. This conversion reduced muzzle velocity from 850 meters per second for the 15mm down to 700 meters per second for the heavier 20mm shell. Lower velocity meant less kinetic energy at impact. Less energy meant poorer armor penetration. The trade-off was considered acceptable because the 20mm high-explosive shells were devastating against unarmored targets. A single hit could tear off a wing panel, destroy a control surface, or blow apart an engine cowling. German doctrine emphasized destroying enemy aircraft with explosive damage rather than punching holes through armor. The Americans had taken a different approach. The 50 caliber Browning was optimized for high velocity and sustained fire muzzle velocity of 2,930 feet per second. That translated to roughly 885 meters per second, faster than the German 20mm by a significant margin. The 50 caliber API round maintained that velocity better over distance because of its superior ballistic coefficient. The hardened steel core of the M8 API round was also designed specifically for armor penetration. American metallurgists had developed steel alloys with exceptional hardness that could withstand the shock of impact without shattering. The core would punch through armor, then the incendiary compound behind it would ignite, setting fire to anything flammable on the other side. This combination gave the 50 caliber API capabilities that exceeded its size category. It was not as good as a dedicated 30mm armor-piercing round, but it was better than many 20mm rounds, including Germany's own MG151 20mm AP ammunition. The test engineers at Tarnewitz understood immediately what this meant. German fighters using 20mm cannon were not necessarily better armed than American fighters using 850 caliber machine guns. In fact, for targets with armor protection, the American weapons might be more effective. The initial test report was completed on August 20th, 1943. It was classified Geheim, secret, and distributed to Luftwaffe weapons development offices, fighter command headquarters, and aircraft manufacturers. The report contained detailed tables showing penetration performance at various ranges and angles. It included comparison data against German ammunition, and it concluded with an assessment that would trouble senior officers. The assessment stated that American 50 caliber armor-piercing incendiary ammunition demonstrated penetration performance superior to German 20mm MG151 armor-piercing ammunition against steel armor plate at combat ranges. This represented a significant capability that German pilots should be aware of. Aircraft with 20mm armor protection could not be considered immune to American 50 caliber fire. The report did not claim American weapons were superior. Overall, German 20mm high-explosive ammunition was far more destructive against unarmored structures. A single Meningeschoss mine shell from an MG151 could carry 18 grams of high explosive, enough to tear apart a wing spar or destroy a fuel tank. The American 50 caliber API carried only about 1 gram of incendiary material. For raw destructive power, the German 20mm was better, but for penetrating armor, the American 50 caliber API was winning, and that had implications for combat tactics, aircraft design, and strategic planning that went far beyond simple ballistics data. German fighter doctrine in 1943 emphasized heavy armament. The Messerschmitt Bf-109F and later models carried a single 20mm or 30mm cannon firing through the propeller hub, plus 2 rifle-caliber machine guns in the cowling. The Focke-Wulf 190A typically carried 2 20mm cannon in the wing roots and 2 rifle-caliber guns in the cowling. Some variants carried 4 20mm cannon. This armament was designed for bomber destruction. A few hits from 20mm or 30mm high-explosive shells would catastrophically damage a B-17 or B-24. German pilots were trained to make quick passes, get solid hits, then disengage before American escort fighters could respond. The heavy cannon gave them the firepower to cripple or destroy bombers with short firing bursts. But this doctrine assumed German fighters could approach bombers without being shot down by defensive fire. That assumption was increasingly questionable. American bombers bristled with 50 caliber machine guns. A B-17 carried 13 guns. A B-24 carried 10. These guns were positioned to provide overlapping fields of fire covering all approach angles. American bomber crews learned to fly in tight formations where each aircraft's guns could support neighboring aircraft. The combat box formation put dozens of 50 caliber machine guns within range of any German fighter making an attack run, and many of those guns were loaded with API ammunition. The Tarnewitz test results meant that German fighters with 20mm armor plate protecting the pilot were not safe from defensive fire. A burst of 50 caliber API could penetrate cockpit armor, wound or kill the pilot and destroy the aircraft. The extra weight of armor that German fighters carried for protection was not providing the expected benefit against American weapons. This revelation came at a critical time. By August 1943, the combined bomber offensive against Germany was accelerating. American 8th Air Force bombers were striking targets deeper into Germany. British Bomber Command was devastating German cities by night. The Luftwaffe was losing experienced pilots faster than training schools could replace them. Fighter losses over Germany were approaching unsustainable levels. The Battle of Hamburg in late July and early August 1943 had seen Luftwaffe day fighters suffer heavy losses. Operation Gomorrah, the firestorm bombing of Hamburg, destroyed much of the city, but it also demonstrated that concentrated bomber streams protected by fighter escorts could overwhelm German defenses. The Tarnewitz test report circulated through Luftwaffe Command during this period. It reached fighter group commanders, aircraft designers, and strategic planners. Some officers recognized the implications immediately. Others dismissed it as technical minutiae that did not change operational realities. But the data was undeniable. At Rechlin, the Luftwaffe's central test facility, engineers had been conducting their own evaluations of captured American aircraft. Test pilot Hans-Werner Lerche had flown numerous captured Allied fighters and bombers, including P-47s, P-51s, and B-17s. His reports described American aircraft as well-built, practical, and effective. Lerche had noted the devastating firepower of American fighters. 8 50 caliber machine guns on a P-47 could put out an enormous volume of fire. The rate of fire on the AN-M2 aircraft version of the Browning was 600 to 800 rounds per minute per gun. 8 guns meant potentially 6,400 rounds per minute, even accounting for realistic burst lengths and convergence patterns. That was overwhelming firepower. German fighters typically carried 200 rounds per 20mm cannon. At 750 rounds per minute cyclic rate, that was only 16 seconds of firing time. In practice, pilots fired in 2 to 3 second bursts to conserve ammunition, 4 to 6 bursts per mission before the cannon ran dry. American pilots with 50 caliber guns had much more ammunition. The P-47 carried 425 rounds per gun for the inboard guns and 270 rounds per gun for the outboard guns, enough for extended engagements. The combination of higher ammunition capacity, faster firing rate, and, now confirmed, superior armor penetration made American 50 caliber armament more effective than German planners had assumed. Captured ammunition tests at Tarnewitz had quantified what combat reports were suggesting. American fighters were deadly opponents, but what could be done about it? German industry was already operating at maximum capacity. Aircraft production was prioritized. Ammunition factories were running constantly. Raw materials were scarce. Changing armament philosophies would require retooling factories, redesigning aircraft, and retraining pilots. None of that could happen quickly. Some Luftwaffe officers advocated for heavier armament as the solution. If 20mm cannon were insufficient, install 30mm cannon. The MK108 30mm cannon had been introduced in 1943 as armament for the Bf-109G and later models. It fired a 330-gram shell with devastating explosive power. 3 to 4 hits could destroy a heavy bomber, but the MK108 had significant drawbacks. Muzzle velocity was only 540 meters per second, much slower than the MG151 MG15120. This created a curved trajectory that made accurate long-range shooting difficult. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The gun was also heavy and carried limited ammunition. 60 rounds was typical, and the slow-moving shells were easier for enemy pilots to evade. Other officers argued for improved armor. If American 50 caliber API could penetrate 20 millimeters, increase armor thickness to 30 millimeters or more, but additional armor meant additional weight. Heavier fighters had reduced performance, lower climb rate, lower top speed, reduced maneuverability. These were unacceptable trade-offs when German fighters already struggled to catch American bombers at altitude. A few engineers suggested Germany should develop its own high-velocity, armor-penetrating machine gun ammunition, copy the American approach. But Germany had committed to the 20mm and 30mm cannon doctrine. Changing course in mid-war was practically impossible. The industrial base was optimized for current production. Ammunition plants were manufacturing millions of rounds for existing weapons. Conversion would take years. The practical response was to inform pilots of the threat and adjust tactics accordingly. Luftwaffe fighter training began emphasizing the danger of American defensive fire. Pilots were instructed to avoid prolonged approaches where bomber gunners could track them. Attack from ahead or below where fewer guns could engage. Break away quickly after firing. Never assume armor would protect them. These tactical adjustments helped somewhat, but they could not overcome the fundamental problem. American bombers were heavily armed with weapons that could kill German fighters. As bomber formations grew larger and fighter escorts became more numerous, the odds shifted decisively against the Luftwaffe. The test results from Tarnewitz also influenced aircraft design. New fighter projects incorporated thicker armor in critical areas. The Dornier-Du 335 Fiel heavy fighter, introduced in late 1944, had armor protection exceeding 30 millimeters in some locations. This was partially in response to data showing 20mm armor was insufficient. But by late 1944, the war had turned decisively against Germany. Allied air superiority over Europe was complete. German fighter production could not keep pace with losses. Fuel shortages grounded many aircraft. Experienced pilots were dead or captured. New pilots with minimal training were thrown into combat and killed quickly. The superior armor penetration of American 50 caliber API ammunition was just one factor among many. But it mattered. Every small advantage accumulated. Better ammunition, more ammunition, higher firing rates, longer ranges. American fighters had all of these advantages. German fighters had courage and desperation, but those were not enough. Production statistics tell part of the story. American factories manufactured over 4 million M1 Garand rifles during the war. They produced over 3 million Browning M2 heavy machine guns in various configurations. They manufactured billions of rounds of 50 caliber ammunition. The St. Louis ammunition plant alone delivered over 6 billion rounds of 30 caliber and 50 caliber ammunition. German ammunition production was substantial but could not match American output. Luftwaffe fighters expended approximately 80 million rounds of 20mm ammunition during the war. That sounds impressive, until compared to American air-to-air expenditure of 460 million rounds of 50 caliber ammunition in the European theater alone. The difference was industrial capacity. American factories were safe from bombing. They had unlimited access to raw materials. They employed millions of workers, including women and older men who would never serve in combat. Production lines ran 24 hours per day. Quality control was rigorous. Ammunition was tested, inspected, and delivered in massive quantities. German factories faced constant bombing. Raw materials were scarce. Skilled workers were drafted into military service. Forced labor from occupied territories was unreliable. Quality control suffered. Ammunition production declined as the war progressed, while demand increased. By 1944, Luftwaffe units were experiencing ammunition shortages. Fighters went into combat with partially loaded guns. Training flights were cancelled to conserve ammunition. Some units resorted to mixing ammunition types in belts, reducing effectiveness. German pilots fought with one hand tied behind their backs. American pilots, by contrast, rarely worried about ammunition supply. If they returned from a mission, their aircraft would be rearmed completely before the next sortie. Ammunition was plentiful. The 50 caliber API rounds that had performed so well in the Tarnewitz tests were available in unlimited quantities. The Tarnewitz test engineers continued their work throughout 1944. They evaluated new German ammunition types. They tested captured Allied ammunition whenever it became available. They provided data to support weapons development programs. But their findings could not change strategic realities. One test from March 1944 examined American 50 caliber incendiary ammunition against self-sealing fuel tanks. The engineers set up captured American-style tanks with rubber self-sealing material and 20mm armor backing. They fired 50 caliber API rounds at the tanks from various ranges. The results were sobering. The API rounds penetrated the armor backing, punched through the self-sealing material, entered the fuel space, and ignited. The incendiary compound worked exactly as designed. The self-sealing fuel tanks that protected many German aircraft from rifle caliber and some light cannon fire offered no protection against American 50 caliber API. These findings were documented and distributed. Aircraft designers noted them. Fuel tank protection schemes were revised. But again, implementing changes required time and resources that Germany did not have. Most German aircraft continued flying with fuel tank protection that was inadequate against American 50 caliber fire. Intelligence reports from late 1944 revealed another troubling development. American forces had introduced an improved API round, the M20, which combined armor-piercing and incendiary capabilities with a tracer element. This allowed gunners to observe their fire while simultaneously attacking armored targets with incendiary effects. The M20 used the same hardened steel core as the M8, but added a tracer compound in the base of the bullet. The tracer burned brightly enough for the gunner to see the projectile's trajectory at ranges up to 1,800 meters. This made accurate fire much easier, especially for bomber defensive gunners engaging fast-moving fighters. German test engineers obtained M20 ammunition from crashed American aircraft in late 1944. They conducted penetration tests at Tarnewitz. The results confirmed that the M20 performed similarly to the M8 against armor, with the added benefit of the tracer element. German fighter pilots now faced API rounds that could be aimed more accurately and still penetrated their armor protection. By early 1945, the Luftwaffe was collapsing. Allied bombing had destroyed much of Germany's industrial capacity. Fuel production had been devastated by attacks on synthetic oil plants. Fighter aircraft sat on the ground for lack of fuel. Pilots with minimal training flew hopeless missions against overwhelming odds. The Tarnewitz test facility continued operating until April 1945. In the final months of the war, engineers tested experimental weapons and ammunition that would never see production. Prototype guns, experimental armor-piercing ammunition, rocket-assisted projectiles. Most of these programs were too late to matter. American fighter bombers attacked Tarnewitz in May 1944. The raids did not completely destroy the facility, but they damaged buildings and killed personnel. Test programs were disrupted. Some equipment was relocated to safer locations, but the work continued because there was no alternative. On May 2nd, 1945, Soviet forces reached Rechlin. American troops were approaching from the west. The Luftwaffe garrison at Rechlin destroyed remaining aircraft and equipment before withdrawing. The Tarnewitz facility, located nearby, was similarly evacuated. Engineers burned classified documents. Equipment was sabotaged. Test specimens were destroyed. Soviet forces captured what remained. They found extensive documentation of German weapons tests, including the reports on American 50 caliber ammunition penetration performance. Soviet engineers were interested in this data because they were developing their own aircraft armament. The information was studied, translated, and incorporated into Soviet weapons development programs. After the war, captured German test data was analyzed by Allied intelligence teams. American ordnance officers were particularly interested in German assessments of U.S. ammunition performance. The Tarnewitz reports on 50 caliber API penetration confirmed what American designers had intended. The M8 API round was an effective armor-defeating weapon. The data was used to validate American ammunition specifications. It was also used in post-war ammunition development. The 50 caliber Browning remained in U.S. service for decades after World War II. The M8 API ammunition continued to be manufactured and improved. Later variants incorporated tungsten cores for even better armor penetration. German recognition of American 50 caliber capabilities influenced post-war European ammunition development. NATO standardization efforts in the 1950s considered various machine gun calibers. The American 50 caliber, now designated 12.7 millimeter, became a NATO standard for heavy machine guns. But the wartime significance was more immediate. From August 1943 onward, German engineers and commanders knew that American 50 caliber armor-piercing incendiary ammunition could defeat armor protection, that their own 20 millimeter cannon could not reliably penetrate. This knowledge influenced tactical guidance, aircraft design priorities, and strategic assessments. It did not change the outcome of the war. German defeat was assured by many factors: industrial capacity, manpower, strategic errors, and Allied determination. But the superior performance of American 50 caliber API ammunition was one more advantage in a long list of Allied advantages, and every advantage mattered. The engineers who conducted the August 1943 tests at Tarnewitz were professionals doing their jobs. They measured penetration, recorded data, and wrote reports. They did not editorialize. They did not claim defeat was inevitable. They simply presented facts. Those facts told a story that German command did not want to hear. The Americans had built ammunition that outperformed German equivalents in a critical category: armor, penetration. The ammunition was manufactured in enormous quantities. It was supplied to every aircraft, every gun, every unit. American pilots and gunners fired it with confidence, knowing it would penetrate targets that should have been protected. German pilots faced that ammunition every day. They knew the cockpit armor might not save them. They knew that self-sealing fuel tanks might not prevent fires. They knew that American defensive fire was deadly. And after August 1943, German engineers knew why. The tests at Tarnewitz had quantified the threat with scientific precision. The reports gathered dust in filing cabinets. Engineers moved to other projects. The war ground on, but the data remained. 20 millimeter armor, 300 meters, 60 degrees. American 50 caliber API, full penetration. German 20 millimeter AP, 10 to 12 millimeters maximum. The numbers spoke for themselves. Sometimes wars are won by grand strategies and brilliant generals. Sometimes they are won by logistics and industrial capacity, and sometimes they are won by engineers who designed a bullet that could punch through armor that enemy weapons could not defeat. The American 50 caliber armor-piercing incendiary round was not the weapon that won World War II, but it was one of thousands of small advantages that accumulated into overwhelming Allied superiority. German test engineers at Tarnewitz discovered this in August 1943. They documented it, reported it, and watched as the war continued toward its inevitable conclusion. The better ammunition would not save lives or change outcomes. It would simply kill more efficiently, penetrate more reliably, and demonstrate once again that American industrial might could produce not just more weapons, but better weapons. That was the lesson of the Tarnewitz tests. That was the reality German engineers confirmed with captured ammunition and steel plates and careful measurements. And that was the truth that 1943 Germany could acknowledge, but could do nothing to change. The Americans had built a better bullet, and they had billions of them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.